Good morning and welcome to the Black Hills Digital Mapping Association conference. Today we're going to get together and we're going to ask that big question.
What's wrong with Web Mercator?
Well, that's kind of part of our problem. We have this round Earth. We need it to be flat so we can do analysis and do mapping. And we kind of put things out there, and unfortunately, sometimes it doesn't work so well. See, my orange peel broke. That's because the issue that happens is that you can't really fit a round Earth onto a flat plane, even though you kind of need to for convenience and to easily make a map we can flatten out. So projections are a way to take that round Earth, of course, and put it onto a flat plane. We do it for lots of reasons. Usually it just makes a lot of things that we do much more convenient and easier. However, we got to pay for it. There are all kinds of distortions we can have, but if we don't have a distortion, we would have things that are conformal, which is true shape, equivalent, true area, equidistant, true distance, and equidirectional, true direction. And a projection can't do all these things. So we always do a compromise to make that work, or the map just won't be flat.
What's the matter with Web Mercator?
So we kind of get on this, and we basically need to make some compromises to make this thing work. There are different kinds of map projections we use to solve different kinds of problems. They all have different properties, and have some of these. So they have different kinds of errors, but none of them are perfect. They're useful for different things. If we need equal area, we need equal distance, we'll choose different map projections. Of course, Mercator there on the right is a very, very common one. And it was, imagine one thing you could think about these map projections is notice the cylinder we're projecting onto. There's an area there where the globe and the cylinder are right next to one another. And those are the places where that map projection has the minimum distortion. So you kind of want to set things up so the area that you're interested in is where those things are. It doesn't work so well with the world map. And you can see terrible distortions, especially with Mercator projection, as we often see.
Are you saying the map is wrong?
Oh dear, yes.
So as you know, the Greenland and Africa is kind of the famous one. Things get far away from the poles and the areas get terribly distorted in Mercator projection. And there are a couple ways to deal with that. Mercator is so handy because north is up, and it's very easy to find your way around on a Mercator map. But these distortions are pretty bad. Here's a $10 word for you, Tissot's indicatrix. Indicatrix, shown in Mercator projection here. It's a way to look at how distortions show up in map projections, both shape and area. And imagine taking a graphical compass, one of those things that you used in grade school with an angle on it, and scribing circles onto a globe, and then imagine taking that out and flattening it all out into a map projection, and that's what you see. So this shows you very clearly how area gets distorted and the XY's calculated for a Mercator projection. So you can see if you're calculating area, you get away from the equator, kind of bad things happen to you. But note, shape is okay as long as it's in a local area, then you're all right. But not so great for world maps, as our friend Mercator can say, for sure.
Well, sue me. I was making good money making nifty globes and astrolabes. I developed a beautiful and accurate heart-shaped map of the world, and even coined the term atlas for my map books. But one cold day in 1569, a drunken sailor wandered into my Duisburg studio, waving a loaded arquebus and demanding a map with lines of latitude and longitude at right angles. Before I knew it, everyone was using cheap rough-offs of my work to cross oceans, and they all blamed me for making Greenland and Antarctica too big. It just isn't fair. I've really had it.
Well, that Mercator projection has become very, very useful. It's been used lots of ways. And one way you can avoid problems with it is to stay near that red line. So around the equator, that's handy. So if we just use the Mercator projection around the equator, everything would be fine. But one option that's been done on that is to take the cylinder and tilt it all the way sideways to make what's called transverse Mercator. And you probably know about UTM coordinates. And what they do is if you tilt things over, you can see that red line is now north-south line. So that's a little more useful. So if you stay within a 6-degree extent, we call that a UTM zone, of course. you can go in and things are pretty good. Area is good, direction is good, shape is good, but you need to stay on that red line. You got to stay in your zone, then you'll be okay. In some situations, people have taken that cylinder and tilted it. So, for example, the state plate zones in Alaska use transverse Mercator, but at oblique. It's actually oblique Mercator. Things have been turned because that's worked pretty well for them. But for world maps, Mercator gets in trouble, largely because those things, once we get to the poles, that distortion gets out of control. We get so far from that red line. Here's another picture of that indicatrix. Now remember, things are pretty good if we can stay near the equator, but of course we don't, especially on a world map. But those shapes, those circles, are pretty good as long as you stay local. So there's some KB articles on the Esri website that are really helpful about this kind of thing, about using certain tools that measure area and distance. Think of tools like near and point distance and things like that. Then there's another one about something called the calculate geometry tool, which calculates areas for polygons or lengths for lines. And you can get the incorrect results if you don't do it right. And these KB articles are really, really helpful, and I have some links to them toward the end. But the key thing, we can avoid these problems we're having with Web Mercator or any kind of Mercator by using some other projection or some other method. One thing to keep in mind is that a lot of tools can work with us. There are solutions to these problems, and a lot of it just has to do with paying attention to what you're doing and learning, understanding coordinate systems pretty well. So read the help. A lot of tools have options to calculate areas and distances in different ways. So for example, you can go ahead and calculate that area with the calculate geometry tool. If your data is in WebMercator or your data is even in decimal degrees, you can tell the tool to calculate using UTM or some other appropriate coordinate system in that area. Some tools have been updated to actually use distances and areas along a sphere. Those are called geodesic areas and geodesic lengths. And so the idea is you measure on that spheroid we were talking about. And some tools you're kind of stuck. You got to read the fine manual, but to get the right result, sometimes with some things like spatial joints, for example, you got to have all your data projected in the same coordinate system so everything will work correctly. And you should choose a coordinate system that will preserve distance, for example, for that spatial joint tool. But documenting is really important. It's all about the metadata. When you give somebody XY coordinates, make sure you give them the coordinate system, both the projection and the datum, or you'll be in trouble.
So, what's so wrong with WebMercator?
Yes, with that web version of Mercator, we do have an issue. Web Mercator is based on a sphere. Remember Web Mercator Auxiliary Sphere? It is based on a sphere. That was done to make the coordinate calculations simpler, but it can get us in big trouble. So it's a big concern because, of course, the Earth is not round. It's an ellipsoid. It's even worse than that. It's lumpy. The geoid is the surface of equal gravity around the world. If you filled up the world with water, that surface would be the equal gravity surface, and that would be the geoid. That gets mapped onto a spheroid so we can do mapping onto a nice mathematically smooth surface. And that's how that works. So that irregular shape is based on the gravity differences around the Earth. The crust of the Earth varies in density and all kinds of weird stuff goes on. But we need to put things onto that nice smooth mathematical surface. That's where our coordinates of latitude and longitude come from. They're always based on a certain shape of the Earth. And we need to make sure we document that, as I was kind of getting to before. And that's what the datum is all about. So that datum is an approximation of the Earth's shape that maps that geoid to a certain spheroid or ellipsoid. And the idea is you want to best fit between those two. You might have heard of NAD 83 and NAD 27. Those are local datums that are a good fit of that lumpy surface to the spheroid there in a local area. But we often, for world maps and for world applications like a GPS device, we use a geocentric or world-centered datum. Probably the most popular one we know about is WGS 84 It's important documentation again. Make sure your GPS, if it's set to WGS84, make sure and make a note of it. So when you give those XYs to somebody, you'll know which datum they refer to. So here is that problem. The National Geospatial Intelligence Agency (NGA) had a real problem with this and started basically making some policies back in 2014 because they were very concerned that people were going to get in trouble. And the biggest trouble is documentation. If you have Mercator coordinates, you better know they're based on that sphere instead of the spheroid, or you're going to end up in the wrong spot. Here's an example of the boundary of the British Isles being way off if you think it's those coordinates mapped to a sphere instead of a spheroid. And it's not that it's really wrong to use a sphere, it's that you just need to make sure it gets documented. If you don't, you run into problems like this. And you can imagine the NGA was kind of concerned about that because in military applications, you kind of want the missile to land where it's supposed to land, or whatever. You want the plane to fly where it's going to fly, and you better not be 33 kilometers off or you're going to be in kind of big trouble. So it's important, and so they kind of banned the use of Web Mercator within NGA, and they kind of come in and then they made a lot of public announcements and they kind of got the word out. But the world is still going to be in Web Mercator because that's kind of the standard that's been built for web mapping. So, but within the military, they're pretty much not using Web Mercator anymore because they've set the policy to do that. Probably because of the big danger of having your Web Mercator coordinates not documented as Web Mercator and you treat them as regular Mercator, and then you're in trouble. EPSG is a group that controls a database of coordinate systems on a website called spatialreference.org, which is a good one to know about because it's kind of a list of all the coordinate systems people use. And it's really useful, and they have some strong feelings about this too. And so they've had some harsh words for Web Mercator, but I'm afraid we're kind of stuck with it. Fortunately, there are lots of resources to help us get this straight. Esri had some guidance they posted for Department of Defense users to make sure that they did things to comply with their standards. Most good GIS systems can handle this. You just need to document what you do and do the right thing. So, what shall we do anyway? Well, RTFM, of course, read the fine manual. When you're doing a calculation or using a tool, what coordinate system is actually being used for a calculation? Does it have an option to use another one? Can we use a projection? Can we do a geodesic calculation? That's going to vary tool by tool. And the other thing you want to really keep in mind is that you want to phonetically document the coordinate systems you're using, including the datums that you use. Not just a lat long, decimal degrees, or UTM coordinates, but also the datum that shape of the earth is based on. Because if you have to guess, really bad things can happen. For example, UTM coordinates are measured all the way from the equator up to where we are in North America. That you can, even though the datum shift may not be very much in decimal degree space, when we're measuring distances and the shape of the Earth is that different all the way from the equator to here, you can be hundreds of meters off and get in pretty big trouble. And that British Isles example was a really good extreme example of what can happen if you don't document what your coordinates, where they actually came from. Okay, so I have a slide here with some further reading. A lot of the things I had slides reference some of these useful sources. One I want to point out is a book by Margaret Mayer from Esri Press called Lining Up Data, 3rd edition. It's actually a very good way to learn about coordinate systems and how to solve specific problems that come up with them. And of course, John Snyder's great book on flattening the Earth, 2,000 Years of Map Projections. It's a real masterpiece and quite a really awesome, interesting book. So one more time we ask ourselves,
what's the matter with Web Mercator?
And the answer is nothing's really wrong with it, as long as you're using it appropriately for what it's for. It's really great for finding your way to the coffee shop, not so great for spatial analysis. So have a great day, and thanks for joining us.
Curtis, that was excellent. I especially like your use of theater in your presentation. This is a really important topic, and I know in coursework we focus on it, coordinate systems and projections. And so if anyone has questions about that, post them in the chat. But something I'm curious about is there's word on the street that we might be getting new projections in South Dakota.
That's true. That's kind of exciting. I talked about I mentioned briefly the two datums, NED 27 and NED 83, which are they're basically shapes of the Earth that everything used to be built on. You may be familiar with the USGS quad sheets, where there's a boundary on the quad sheet that's an NED 27, and then there are new ticks on there that are the lat longs and NED 83. Okay, and there was about what 60 years in there in between. And about another 60 years has gone by, and it's time for a new datum. That NED 27 datum was all based on land measurements. They basically, everything was tied to a spot in Meade Ranch, Kansas, right? And NED 83 is based on satellite measurements, so it's really very accurate. It's tied to the center of the Earth within about 2 centimeters. And that means the ellipsoid's kind of moved around, but it's optimized to the geoid to make North America fit really well. So you wouldn't use NED 83 in Africa because it would be way wrong. You'd use a world-centered datum. And one thing about NED 83 is it's kind of tied to the North American plate. If you do the geodesy, you cross the boundary of the San Andreas Fault, and all of a sudden your accuracy goes out the window. And that's because all these plates are moving around all the time. And even with NED 83, they have a thing called an epoch, where you can dink around and have different parameters where they move the thing around as the plates move around, and as, of course, more data comes in. But there's a new thing coming, the North American Terrestrial Reference Framework. NATRF 2022 is going to be the next thing, and that's coming at us. And I think we're going to see it, people locally, where you're really going to see it is we'll have new state plane zones. And one thing I'm excited about is this is an opportunity to kind of redo it. Kind of like ArcGIS Pro is a chance for Esri to start from scratch. This is a chance for the NGS to kind of come up with a new system that's more accurate and more flexible. So NATRF 2022 will, instead of kind of epochs in time, it'll actually you can type in a date and it'll give you locations for that date as the plates move around. So that's kind of neat. And locally, we'll have new state plane zones. So we'll have for kind of medium scale use, we'll have a state plane zone for the whole state. It'll be accurate enough for that. But for things like property and survey grade stuff, we'll have, I'm trying to remember how many zones, maybe 15 zones or more, that'll be super accurate. But if we're doing regional analysis, we can just have to worry about one state plane zone, which will be kind of nice. And even in the older state plane zones that are in use now, some states said, to heck with it. Montana, Nebraska, they only have one state plane zone, but we'll have a new one in South Dakota, and we'll actually have several, copies of them, and they're going to tweak the parameters in various ways to be as accurate as possible. So the future of coordinate accuracy is bright. Anyway.
So that should eliminate some of these issues you talked about with Web Mercator. It's primarily the geometry, or not eliminate, but simplify.
Yeah. Well, the thing about Web Mercator is it's based on a WGS 84 datum, and I'm thinking they'll probably stick with that for a long time. And the issue with Web Mercator is that it's designed for very fast calculation between XY and lat long. But the lat longs it's based on are based on a mapping from the geoid to a sphere. So even if you went with the NatRF is really a thing that's in our part of the world for surveying and things like that. And we're really talking about some of the big problems with Web Mercator have to do with when you make really big world maps. As a matter of fact, one reason Google used it is that when you're looking at buildings, you want a square building to stay square. And that's going to happen pretty much anywhere in the world with Web Mercator. The scale may get all screwed up, but the shape will be pretty good. But they took some shortcuts. You saw that thing where you had one less trigonometric thing you got to do to get from XY to lat long. And so, yeah, we're kind of stuck with it. But I think the important thing to keep in mind is with all these map projections, they're all compromises. And Web Mercator has its issues, and you got to be very careful with analysis. I mean, I really discovered it when I was digitizing areas in Pro right on the screen, and my areas were wrong. And that's because that base map is in Web Mercator. And so you need to keep that in mind. And tools keep getting added. You know, it's really important to read the help. I mean, one thing with my students, one thing we do a lot is I'll give them an exercise, and part of the lab is to read the
We may have,
fine
at
manual.
least I've lost it on my end.
I'm excited. If you want to know more about this NATRIF thing that's coming up, which is kind of cool, Linda Foster is working on that committee statewide from Ferber Engineering, and she's one of our board members. And that's one cool thing about being on the board is you get to know all these people, so you're in the loop. It's important.
That is the truth. One of the biggest things I've learned, and for some of the newer ones here at the meeting, is just the geodesic, using geodesic calculations for geometry can solve a lot of those issues regardless of what coordinate system you're using. But when you make that mistake, you find out fast, let's put it that way. You tend not to make it after that point. No, coordinate systems are so important. Like, you're never going to get away from using them in your career. You need to have a good understanding of them. So thank you for sharing that information, Curtis.